Okay, I'm going to make it start. So, hello everyone. So thank you for joining this webinar. I'm Pierre. I'm Associate Professor at the UCL Division of Surgery and Interventional Science. So I'd like to thank Carol and Zoe from the UK Acoustics Network for their kind invitation. And I'm going to discuss with you an overview of OptimUS, a fast computational solver for biomedical ultrasound and acoustic applications. OptimUS essentially uses a novel implementation of the boundary method. And this is in the form of a Python library, and it represents the outcome of a cross-faculty and cross-institutional collaboration involving UCL Mathematics, Mechanical Engineering, Division of Surgery and Interventional Science, Cambridge Engineering, and Pontificia, Universidad, Católica de Chile. So, first of all, a bit of the content I'm going to broach with you. I'm going to first discuss the background and context, which arose for essentially biomedical ultrasound applications, more specifically therapeutic ultrasound. Give you a brief overview of our implementation of the boundary method, and also give you an overview of OptimUS, the Python library, with transcranial ultrasound examples. I'll review some other therapeutic ultrasound applications, go into a sound and air application involving in-utero sound transmission. And we're going to discuss how we can broach piecewise heterogeneous domains as well as acoustic nonlinearity, discuss strengths and limitations, and finally conclude. So I think some of you in the audience have a background in biomedical ultrasounds, but some of you may not. Essentially, ultrasound can induce a host of biophysical effects inside the body, and these can be harnessed for therapeutic purposes. So at lower levels, you may get cytoskeletal disruption, so basically disruption of cells, mild hypothermia, and as you increase drive levels in transducers, you can induce thermal ablation of tissue, as well as mechanical fractionation, a process known as histotrypsy. Focused ultrasound has the advantage of being non-invasive and non-ionizing, and it's been gaining quite a bit of traction in both treatment of neurological conditions and in the field of cancer therapy. And broadly, we divide the biophysical effects as thermal or non-thermal. And here in the slide, you can see an example of a focused spherical section transducer, two examples. And this is a simulation of one of those fields. And you can see that we're focusing the beam in a tight region. And if you increase drive levels, you can effectively coagulate tissue by converting mechanical energy into heat. So over the past 20 years or so, there's been gradual approval of this modality for a range of conditions. So this is in the US with the Food and Drug Administration, but the National Institute of Care Excellence in the UK has generally followed suit closely behind. In 2004, we had approval for uterine fibroids, then palliative care of bone metastases, treatment of prostate cancer, essential tremor being, unlike Parkinson's disease, a tremor that's caused for generally somewhat unknown reasons. Parkinson's disease, osteoblastoma, and more recently, liver tumors using histotrypsy. So for those of you unfamiliar, the way in which this generally takes place is you do this under magnetic resonance imaging guidance. Here you can see you have a patient that's about to be inserted into an MRI, and that helmet is actually an ultrasound transducer involving 1,024 elements, which focus towards the center of the brain. This is the Insight-X system for essential tremor. And there's a range of conditions here. This is taken from the Focused Ultrasound Foundation, and these conditions are at various stages of clinical translation. So, okay, that's all great, you might say, but nevertheless, there's still a lot of challenges that we face, and we characterize devices using laboratory experiments. Here you can see we have a transducer array in a water bath with some rib phantoms. We can use ex vivo and in vivo experiments to look at more specifically biological effects that are induced, and human trials. But nevertheless, there's essentially a requirement to plan intervention before treatment. You can use MR thermometry to a certain extent, but that's not always going to tell you the whole picture. And there's a consensus, I think, amongst our community that we need to use patient data to try and plan the intervention. And that means effectively propagating ultrasound in silico using anatomical data obtained from CT or MR scans. So there's quite a few challenges with this. You have large tissue paths, you have heterogeneity, you have different tissue types, different properties which may be patient specific, and you may want to ablate tumors of various sizes, which may mean overlaying lesions until all your tumors are ablated. You may have large blood vessels, and that can cause convection and essentially drag away the heat from the zone you're targeting. And by and large, you want to ensure that there is a sufficient dose at the target tissue, but you also want to spare healthy tissue. So my opinion, and that of I think quite a few of my colleagues, is that we want optimal treatment planning strategies based on high performance computing methods, and that these are expected to form a vital component of successful clinical outcomes. Okay, so the frequencies we're dealing with in biomedical ultrasound tend to be between 0.5 megahertz and 5 megahertz. And as I mentioned earlier, we have rather long tissue paths relative to the wavelengths involved, several centimeters. So if you look at this diagram here of a penetrable object inserted inside an incident medium, if we have an incident wave, you want to predict what happens. You can do that fairly easily. So using a range of methods at lower Ka, but as you increase the dimensions relative to the wavelength, all sorts of things happen. You can get long computational times, dense computational grids. In some cases, if you have high contrast between the exterior medium and your objects, then that can cause issues. You may require mesh refinement, but also there are some limitations with some methods, as we'll see in a bit, involving numerical dispersion pollution, which means that as your Ka goes up, it becomes increasingly difficult to get close to the solution to your problem. So there's some individuals that may use general purpose solvers such as ANSYS or COMSOL, and they definitely have their use, but there can be lack of software traceability in these solvers, and also they may not always have undergone validation for the application you have in mind. So just some numbers here. If we consider a cube that's 20 by 20 by 20 centimeters, frequencies between 0.5 to 5 megahertz. We have a wavelength which goes from 3 to 0.3 millimeters in soft tissue or water. And if you want a spatial discretization of 10 to 20 points per wavelength, that creates a rather large problem. You're talking about the order of 10 to the power 18 floating point operations per second. So it's not to say it can't be done. It has been done using a range of solvers, but you do increasingly face challenges. For example, with finite difference time domain methods, whilst you have a low implementation effort and you can generally solve whatever equation you like, including nonlinear equations, you still suffer from numerical dispersion, staircasing effects, and when you get dense meshes, it's not always the most efficient way to go about solving a problem. So case-based pseudospectral methods such as K-wave, which is very widely used in the therapeutic ultrasound community, that's substantially more efficient than finite difference time domain. You can carry out nonlinear calculations. It's got, I think, some viscoelastic capabilities as well. But as you increase your Ka, you're going to get numerical dispersion effects, and at high contrast interfaces, you require finer mesh. So by high contrast, I mean, for example, between soft tissue and bone, where you have quite a big jump in acoustic impedance. There's the hybrid angular spectrum approach, so that benefits from quite fast computational time, but due to its nature, it poorly models scattering effects. So there's been some interest recently in geometric ray tracing methods involving diffraction correction. So there's quite a bit of research in France going on. The platform is Viva Healthcare, and that potentially can lead to some short run times and no memory consumption, can model shear waves, but it does rely on approximation. And so I feel we need some full wave solvers to be able to truly validate the range of frequencies over which this is valid. Finite element methods ubiquitously used, so they have the advantage of being able to resolve complex geometries and interactions and to model shear waves and nonlinearities. However, you have large memory requirements, long run times, and numerical pollution effects tend to kick in once your K gets too large. So with all this in mind, we essentially wanted to design a computational platform which would be able to get us close to simulating ultrasound propagation inside the human body, and generally, we know in heterogeneous media, we wanted it to be accurate mathematically, reasonably fast, and the philosophy is to have open source and completely traceable code. And we wanted this also to be used by the non-experts. Myself working in the division of surgery and interventional science, I work with cell biologists, clinicians, and I wanted to be able to give something to my project students where they could, just effectively, run it without too much implementation effort. So this can also serve the purpose of designing transducers for specific applications and to help safety guidelines with ultrasound instrumentation. To do this, we looked at the boundary element methods. I've been working on boundary element methods for over 2 decades, and they have somewhat come a long way. So the idea behind this is that you're solving linear partial differential equations, but you're reformulating them as integral equations. And you're using Green's function of the Helmholtz equation to effectively change your volumetric grid, volumetric problem into a surface integral problem. And if you look at this figure here, you can see a finite element mesh and a boundary element mesh. This is, I should emphasize, this is not actually an acoustics problem, but it tells you a couple of things. First of all, you're just meshing the surface, but also you can tell that the boundary element mesh is coarser than the finite element mesh. And this is something we'll see later on. We can get away with generally coarser grids. So potentially you're significantly reducing the amount of degrees of freedom that you require to solve your problem. So we only need surface meshes. The boundary element method has potential to be highly accurate. We don't know really of any significant numerical dispersion or pollution effect. And we can easily handle unbounded domains because we have a Sommerfeld radiation condition at infinity. That means that you don't have to be concerned about implementing a perfectly matched layer to avoid reflections off the boundary of your computational domain. However, it does come at a cost, high RAM consumption, and it's also challenging to implement. It's unlike finite difference time domain methods. There is quite an uphill struggle to implement such methods. Okay, so I don't want to dwell too much on this, but this shows you the formulation, that's starting point of the formulation. So we're considering piecewise homogeneous domains we have here embedded inside an infinite domain. So we have the Helmholtz equation for the interior domains and for the exterior domains. We have an incident field, which could be anything. It could be a plane wave, it could be a point source, it could be the field of the volt transducer that I showed you earlier. And we assume continuity of pressure and normal velocity at the interfaces. We have the Sommerfeld radiation at infinity, effectively. So yeah, that's the starting point. And there are various representation formulae you can obtain, starting from the Calderon operator. So this is a bit beyond the scope of this talk. I'm happy to take questions at the end, or indeed have point you towards the right papers and have individual discussions with you if you want to find out more about the implementation. But in a nutshell, what we have is once we've taken everything into account, we have a system of linear equations, as we often do in many physical problems. So these are the different boundary integral operators. And you note that the left-hand side matrix is fully populated, contains complex numbers. So you'd say, okay, that's all great. All we need to do is populate that matrix and invert it. The challenge here is that this type of system gets very large for the problem we're dealing with. So you can't have a direct inversion. You have to do an iterative solve using we use the GMRes method. But if you do that, it tends not to converge. So you have to do all sorts of mathematical tricks to make sure that your system is well conditioned, and also to reduce the size of your system. So for this, we developed a dedicated on-surface radiation condition preconditioner. We use H-matrix compression technique, and as I mentioned, an iterative solver. And if we're careful about what we do, we can actually solve some rather large problems with rather limited computational resources. So the novel contributions to our boundary element methods were the dedicated OSRC preconditioner. So also we have a specific formulation which enables us to tackle high contrast interfaces. So I mentioned soft tissue bone, but also, as we'll see, air and soft tissue. And we've provided also a test bed for different types of boundary integral formulations. So we've packaged this into a Python library, which is available on GitHub. I've got the link here, so feel free to download the library. The instructions are there, and if you have any issues, please get in touch with us. I'll put the contact details at the end of the talk. So this formulation works entirely in the frequency domain, which is suitable for quite a few problems in biomedical ultrasound. Whilst we sometimes deal with pulses, we have generally pulse times of several seconds, which means that for all intents and purposes, we have quasi-continuous wave conditions. So the architecture is such that we have shared RAM with multi-core processing. There's cross-platform compatibility using Docker, and we used BEMPP, which is a software library developed by Timo Betje at UCL. So that's essentially what's under the hood. So we can model different types of sources, a point source and a plane wave, and right now we've got a plane circular piston, bowl type source, and also a spherical section array transducer with planar circular elements. So these types of sources tend to be very useful if you want to create some phasing, and as I mentioned earlier in this talk, to try and specifically target healthy tissue and avoid if you want to target pathogenic tissue and you want to specifically avoid healthy tissue. And you can do that by some beamforming, either using time reversal acoustics methods or constrained optimization methods. So these last three types of sources, we're modeling them as basically summation of monopole radiators. So we have a Dirichlet condition. We have looked at imposing a Norman boundary conditions, but that's not yet implemented, but it is technically feasible. So one advantage here is that since we don't have any numerical dispersion, there's no issue of orientation of the source with respect to the computational grid. For example, if you had a volumetric grid and you're using a plane piston type source, what's going to happen is you're probably going to want to place it in either the X, Y, Y, Z, or X, Z plane and rotate your scatter, your object relative to that. Here, that's not really necessary. It's not going to change the outcome of your calculation. So in terms of input, we require 3-noded triangular element surface meshes, such as those that can be generated within Mesh Mixer. And we use a Gmesh file format for input. So here, some anatomical structures, skull slabs, and some ribs. Generally, 3 to 6 grid points per wavelength tend to be sufficient. And relative to other computational schemes, you can get quite accurate solutions with coarse grids. So we've validated this quite extensively on spherical scatters and also concentric spheres. I'll show you a validation exercise that we did on concentric spheres later on. But also we participated in a benchmarking exercise with iTrust, which is working towards safe and effective applications of transcranial ultrasound for ultrasound neuromodulation. So essentially there were a range of participants that contributed different types of simulation methods, and the exercise was led by Brad Treby at UCL. We published the work in JASA, which is reference 8. So ultrasound neuromodulation, it's a growing field. There's growing popularity, and the idea here is that you can carry out deep brain stimulation without having to do it invasively using ultrasound. So maybe some of you have seen this article in The Guardian almost 2 years ago. So there's a lot of this stuff going on, but I think we'll all agree that we kind of need to know what's happening, and therefore modeling as well as experiments are absolutely vital to try and plan an intervention and to ensure that the outcome of the treatment is consistent and patient specific. So some of the participants in the ITROS exercise are listed here, and quite a few computational approaches have been used. Hybrid angular spectrum approach, case-based pseudospectral method as implemented in K-wave, finite difference time domain, finite element and boundary element methods. So I should point out it's actually a spectral element method, but that's a subset of finite element methods. And we looked at a range of idealized geometries, and I think this paper has already had quite a bit of impact. It's been cited, I think, 38 times to date, and I think it was long overdue to have this benchmarking exercise in the community, because a lot of people were putting out results using different solvers and without really carrying out any true validation. So here I'm going to take you through one of the examples, one of the benchmark cases in this paper, which involves the aberration of a bowl source by a cell slab. So this example is available on our repository, and just basically to show you that to set up a job like this, it's actually relatively straightforward. So we import OptimUS. Here I've just starting the importing date time to monitor the runtime for this. So here you can create a bowl transducer by specifying the frequency, radius of curvature, and other parameters. So here we're just setting a parallelization method for the incident field calculation. We specify the material properties for the exterior medium, which is water without attenuation, and cortical bone for the interior medium. We load the grid and we rescale it, and we create the model. And then we solve it. So it takes 3 minutes to solve, 3 minutes and a bit. And what we're solving here is we're obtaining the surface potentials at the so that's the pressure and normal derivative at the vertices of the surface grid. So then what we need to do is we then use Green's function method to obtain what happens in the field. In this instance, it's 141 by 241 Cartesian grid, and then we can plot the real part of the pressure and its magnitude. And here you can see that we have an aberration of the beam. This is the same source I showed earlier, and it demonstrates that in fact the cranium here shifts the location of the focus. So this is something that's quite important to take into account. So this simulation takes 7 minutes and 21 seconds. And I should specify this is on a 512 gigabyte RAM, 32 core workstation. So it's not your average desktop computer, but still, it means you can get these kind of results for this kind of problem reasonably quickly without having to resort to cluster or cloud computing. So another application here is for the kidney. So I showed you the clinical translation timelines for various conditions, and I think there's cancer of the kidney is one of the cancers for which focused ultrasound is getting close to getting regulatory approval. So this is using a 256 element random array at a frequency of 1 megahertz, and we have about a 2-hour runtime on the same workstation. So with RIDS, we have about 1 hour, again 1 megahertz. And another example, this involves osteoid osteoma, which is a benign growth that tends to occur in children in the bone, and which can be rather painful. And MR-guided focused ultrasound is emerging as the gold standard treatment for that. So this shows you the field in the XY plane, and this shows you the geometry of the configuration with the various elements of the array shown in magenta. So I'd like to discuss with you another application entirely. This is in audio range acoustics, and this is looking at in utero sound transmission. So noise exposure during pregnancy can be an issue. You can have occupational noise, workplace. For example, during an MRI scans can be very noisy. High impact sounds such as those that can occur in the gym. London Underground, loud music. It doesn't even have to be modern music. If someone plays in a classical orchestra, the sound pressure levels can be quite high. So there's evidence that the fetus responds to sound stimulus from mid-gestation. And there's been a host of adverse effects reported in the literature associated with sound noise exposure during pregnancy. So that includes premature birth, reduced birth weight, infants with congenital malformation, gestational hypertension, and preeclampsia. So there's some debate regarding the extent of these adverse effects, simply because this involves studies on large cohorts and using statistical methods to try and ascertain what's actually happening, and there may be confounding variables. So there's this requirement to at least try and predict what the mechanical effects of noise actually are. And this may not just be on the fetus's hearing. There's I think a lot of focus on that in the literature, but also on the brain development. Neural tissue is quite fragile. The question is, can sound in external sound sources, can they ever be loud enough? Can they be sufficiently transmitted into the abdomen and into the uterus to actually generate any issues with the fetal development? So to do this, we used OptimUS we developed a nested formulation. Here I showed you some formulation based on piecewise heterogeneous media, which are piecewise homogeneous media, which are immersed in an exterior domain. But here we're looking at domains embedded into other domains, and we're publishing a paper on this, and we're going to very soon push this nested formulation onto our repository. So we validated this using a known analytical solution, volume concentric spheres. And we were fortunate to be able to pair with some scientists at King's College, at University College Hospital, that were able to provide us with scans of pregnant women, MRI scans, which we were able to segment and import into our model. And what we did was predict the transmission of acoustic waves inside the uterus as a function of frequency throughout the audio range between 20 hertz and 20 kilohertz. So initially, we wanted to, as I said, validate the solution. So we took two nested spheres immersed in air. The exterior sphere had the properties of fat, the interior sphere had the properties of bone. So we did a couple of convergence tests, 5 kilohertz and 10 kilohertz, with mesh densities of 3 to 14 elements per wavelength. And we looked at spatially average pressure in the geometric groups. So these are the points that we considered, Cartesian grid, and we're effectively doing L2 norm of the value and looking for convergence. So at 5 kilohertz, what happens? So it reduces quite nicely, but even at 4 elements per wavelength, you can see we've got quite good agreement. You can see someone's raised their hand. I think, sorry. I think the format is I'll take questions at the end, unless you want to put something in the chat. Okay, so if someone wants to put something in the chat now, if that's really important, I'm happy to answer it now. But I'll take questions at the end. Rest assured. Okay, so at 10 kilohertz, we get the same picture, and we have nice convergence, or nice reduction rather, the relative L2 norm. And here's some plots, some beam plots of what happens. So we have the analytical solution of 10 kilohertz relative to the boundary element solution, and good agreement there. And this is at 20 kilohertz as well. So again, good agreement. And this is just using 4 elements per wavelength with a GMRS tolerance of 10 to the minus 6. So we can get away with a relatively coarse mesh, 4 to 5 elements per wavelength. And we initially started this work trying to use FEM, and we quickly realized that even with 4th order elements, there are too many numerical pollution effects to actually do this. So to the best of my knowledge, this kind of exercise would be too challenging using FEM. So the anatomical mesh generation, so as I said, we were fortunate enough to get some segmented MRI data. So the raw data looks like this, which isn't great. I think the resolution was about a centimeter for the voxel size. But we should bear in mind that the wavelength in soft tissue at 20 kilohertz is 17 millimeters. So that's you're probably kind of going to be okay. But nevertheless, we carried out some smoothing. So that's for the abdomen. And this is for the uterus. And we also included the spine inside the calculations. So we had different mesh sizes for different portions of the frequency range. And here are some results showing beam plots and as well as volumetric plots of what happens inside the abdomen, or at least our prediction of what happens. And on 3 data sets, we have this type of a frequency response, but for the transmission. So it's interesting that actually quite a bit of sound tends to get in, and this tends to corroborate in vivo measurements on sheep that we also carried out, which showed that in fact there's quite a bit of transmission inside the abdomen. Okay, so I've got a few minutes left. So before I take questions, I want to briefly discuss with you how we may incorporate nonlinearities and heterogeneities into these models. Right now, we've looked at a piecewise homogeneous media. So we know that BEM is limited to linear problems, and nevertheless, in biomedical ultrasound, particularly in therapeutic ultrasound, nonlinear propagation is a fact of life. And right now, I haven't discussed this yet, but it's important for us to try and incorporate this into our library. And we've made some steps towards it, which I'll discuss now. And similarly, we want to try and, for example, in the case of the cranium, we know that the bone, that there is spatial variation of the material properties, and we want to try and incorporate this. So if we look at this equation here, which is the Westerveld equation, so you'll recognize this portion here, which is the wave equation. Here we have essentially what accounts for dissipative mechanisms in the form of a fractional Laplacian. And on the right-hand side here, we have the nonlinear term. So this accounts for conversion of energy from the fundamental harmonic to higher order harmonics as the wave propagates inside the medium. Now, if we make the assumption of nonlinearity, we can actually rewrite the equation as a set of inhomogeneous Helmholtz equations. So we assume a solution of this type where we have a summation of harmonic pressures for each harmonic, and we can end up with this equation here, well, this set of equations. So that means that if we compute the fundamental, then we can get the solution from the fundamental and compute the second harmonic, third harmonic, fourth harmonic, and etc. And this is what this looks like. This for a bolt transducer. And here we've shown a validation of this against a known simulator called the HITU simulator, which uses another equation, K-Z-K equation, which is closely related to the Westerveld equation. So overall, quite good agreement. So this is for a homogeneous domain. Now we'd like to obviously go towards heterogeneous domains to do this, and there's a way forward. It's, well, basically just getting the time to do it, really. So for heterogeneous domains, here we're assuming that we have one object which is a piecewise heterogeneous embedded in an infinite domain, homogeneous infinite domain, and we're using a combination of a volume integral equation to treat what's happening inside the heterogeneity, with a boundary integral equation, sorry, to treat what's happening externally. So we did some conversion tests on a homogeneous sphere using the volume integral equation approach, boundary element method, and the analytical solution. So we get good convergence. And we also looked at a heterogeneous cube. So again, good results versus BEM coupling. So it's quite encouraging. The one issue we have at the moment is that there's quite a lot of degrees of freedom associated with it. You need all the degrees of freedom of your surface mesh plus the degrees of freedom inside inside your boundary. And however, the convergence is actually quite quick. So we want to explore this further, perhaps look at some matrix compression techniques to reduce the problem size to be able to treat relevant scenarios. So some strengths and limitations of OptimUS. So right now we can solve problems in high contrast media in piecewise homogeneous domains quickly and accurately. We don't require a volumetric grid for this. We don't have to contend with domain truncation effects. We have generally fewer elements that we require relative to other themes, fewer elements per wavelength. And we can do this entirely in the frequency domain, which can be advantageous. So we have no known pollution, numerical pollution and dispersion effects that we know of, and also no staircasing effects. However, we do require quite a large amount of shared RAM, and basically we're still in the process of implementing variations of material properties within a single domain. We're limited to acoustic domains, although we like to try experiments with elastodynamic boundary element formulations to see what we can get with that. And also, due to the nature of the Green's function, the solution close to the boundary can be somewhat inaccurate. We've made some improvements in that. This is also something we'd like to explore. So I'd like to invite you, if you're interested in this, to have a go at our Python library, and quite happy to help you out with this. I've put the link here, as well as an email address for queries, but feel free to email me directly. And I should point out, I should re-emphasize rather that the library has been extensively validated with analytical solutions and other solvers. Work in progress is GPU acceleration, incorporating the fast multiple method for Helmholtz problems to see if we can get any significant advantages relative to what we're using now. And we want to generalize our weakly nonlinear formulation and improve upon our piecewise heterogeneous formulation. Now, also, we've essentially done this within the confines of biomedical acoustics and ultrasound, but there are other applications, other possible applications. So if you think that this can be of use to you, as I said, please get in contact or ask a question now, soon. So I'd like to acknowledge the following sources of funding and also all the individuals who helped out with this over the years. So I'd like to thank you for your attention. I'm quite happy to take questions. So I think the preferred format is to put your questions in the chat. So I see I already have one. Can this be used to produce animation of wave propagation, or does it output a single time produced field of pressure? The answer is yes. I mean, you have this is something actually we've done in one of our Python notebooks. But essentially, yes, if you take if you know your pressure magnitude, then you or rather pressure real part and imaginary part, you can compute the variation with time of the wave. Is it possible to use as a source, custom source with custom directivity? Broadly, the answer I think would be yes. Right now we're limited to monopole sources. So if your source can be described as a summation of monopole sources, this is indeed something that can be implemented. As I said, if it's a combination of monopole and dipole sources, that'll be a bit more challenging in the current implementation. Oh, thanks, Jonathan. That's very kind of you. So, any other questions? Okay, validation in air. So yes, in essence, because the case of the nested spheres that I've provided, that gives you the exterior medium was air. So we had air, yeah, fat, and the inner sphere was bone. So and we had, as you can see, very good agreement with the analytical solution for what was quite a high Ka. So in terms of experimental validation, no, we haven't done any experimental validation in air, but I don't, I mean, if we assume that the Helmholtz equation actually determines your governs your physics, then you should be okay. Oh, thanks, Ben. So, okay, a few more questions here. So yeah, can this be used to simulate a range of frequencies in one pulse? The answer is yes. We have, in fact, an IPython notebook on this very scenario. So there's limited capability. If you want to test it, well, I said limited. In principle, it is feasible, but we haven't extensively tested it for a range of applications. But please feel free to try it out and get in contact if you want to look into this. So how does this compare to K-wave in terms of performance, speed, and requirements memory? So I think this very much depends. In some instances, it can be faster than K-wave, for example, for a skull slab. But again, it depends which implementation of K-wave. I think, you know, for the types of problems that I've shown, it, according to my tests at least, maybe Ben can confirm this. We can be quite a bit faster on the same workstation using the CPU implementation, C++ implementation of K-wave. For GPU, I'm not entirely sure. You need some computational resources, but I think for large problem sizes, you don't always, you wouldn't necessarily need to resort to a cluster. It depends really on the amount of degrees of freedom. For example, if you have a smaller scatter embedded in a very large volume, Optimus is going to be very effective in dealing with that. Oh, Jonathan, yeah. So that's it's a very good point. Okay, so could you say a bit more about what's special about the formulation that allows high contrast ratio, perhaps with regard to the Calvin projection? Okay, so I'd invite you to look at one of our papers. I'll send you the link. It's a bit long-winded to discuss in the context of this webinar. But thanks for your question, and indeed we can can meet up on Teams to discuss this further if you want. Would the method be applicable to longer wavelengths over larger areas? Yes, for sure. In fact, one of my colleagues is looking at an underwater acoustics application of this, which I mean, it's still quite high Ka, but we effectively, lower frequencies, but much longer distances. So okay, so yeah, Jonathan's pointed out that validation of NPP in air with complex force directivity functions in Java. Okay, so that's interesting. Any further questions? Okay, could you put the link to? Oh yeah, okay, right. Yeah, I wouldn't mind a link as well. Actually, that's quite interesting. Okay, thanks, Zach, for your comments about the talk. It's always good to hear that efforts are appreciated within the community. Okay, if there are no further questions, I'd like to thank you all for your attention and your interest in the subject matter. And as I said, please feel free to contact me. I forgot my email address on here. Yeah, here we are. So please feel free to contact me.